All right, guys, so for question 3, it is asking the highest energy conformation for trans 1,4-dimethylcyclohexane has how many HCH3 diaxial interactions? Okay, so first what we need to figure out is what is our highest energy conformation look like for a trans 1,4? And so this is where we're going to be using the chair conformation and figuring out where to put our dimethyls. And so if you're still having a little bit of trouble with figuring out what is cis and trans in regards to um, the chair conformation, easy trick to use is to just memorize this first line. So memorize 1, 2, and know that cis is EA or AE. They're opposites of each other, as where trans is EEAA. Now the only thing you have to do after that is know that they zigzag like this. So if you know the first one, then you can just draw your 1, 3, 1, 4, and then just zigzag them. So if you have EEAE here for cis, just put it over here on the 1, 3, and then put it down here on the 1, 4. And so that's some more space on your note card that you can have if you just memorize that little table. Okay, so what's our highest energy conformation look like? Well, in regards to a chair conformation, we want to know that axial positions are unfavorable for any compounds that we're attaching to the cyclohexane. And so in this case, we can, in a 1,4 trans, we have the option of either having EE or AA. Now the AA, we just said, is going to be our highest energy conformation, so that's what we're going to go ahead and draw our methyl groups. We're going to put them in the axial position. So straight up, I like putting them on the ends because it just makes it easier, but let's go ahead and actually just put them here. Still the same thing, still 4 carbons away from one another. And so this would be our highest energy conformation, both in the axial position. This would have been the equatorial position, but that would have been a lower energy conformation. Now, the thing you need to walk away with this from this problem is that for every compound that you put in the axial position that isn't a hydrogen, you're going to have 2 diaxial interactions. And so what's missing in that word is the fact that it's usually referred to as a 1,3 diaxial interaction. And that's because when you have a compound that isn't a hydrogen in the axial position, there is an interaction that occurs with the third compound away from the axial compound that you've added. And so in this case, we've got our methyl group, and that methyl group has hydrogens floating around it that are now interacting with these hydrogens at the third position. So this would be 1, 2, 3, then 1, 2, 3. And so it's now causing a hindrance and interfering with one another, and that's what a 1,3 diaxial interaction is. And so since we've got 2 methyls in this case, this methyl here will also have 2 1,3 diaxial interactions. In this case, it's going to have them here, and then we got 1, 2, 3 here. And so notice that everything is in the axial position. That's why it's called the diaxial interactions. It's not going to interact with anything in the equatorial positions because everything that's the more favorable conformation. The equatorials do not interact with one another. And so the answer for this case, if we have 2 methyls, if we have 2 methyls on the cyclohexane, and for every methyl compound we're going to have 2 diaxial interactions, the total number of diaxial interactions would be 4.